Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its products and experiences in regional planning and public management. This video is confidential and may not circulate outside the receiving company without HI's authorization. Artificial hypothalamus. The power of today's technology is not in the mathematical calculations that it allows to perform, it is in the mathematical calculations that we can imagine that we can perform. Integrated regional planning. The artificial hypothalamus is the evolution of DSS under the Industry 4.0 revolution, and it is the integration of the methodologies of artificial intelligence and mathematical programming with the modeling of physical systems associated with autonomous and real-time optimization models, which communicate with each other. These system includes inhabitants, facilities, energy, land use, enterprises and industries, and transport and logistics. Cities and regions. Analytics, smart and sustainable. High RPO, regional planning optimization, is a set of mathematical models to support planning regions formed by urban and rural areas with a high degree of integration. The model's mathematical programming are oriented to Project, holistic regional planning optimization. Challenge, to develop a model to support the territorial planning plan of the city of Medellin, to evaluate the impact of land management policies. Solution, design and implementation of a spatial techno-economic input/output model to simulate the future land use, based on maximizing partial social surplus, incorporates the following subsystems: business, housing, public space, employment, and transportation. Result, the model probed that, for the steady-state case, the non-optimality measures were persons relocation, fraction of the relocated population, equal to 62%, and economics relocation, fraction of the relocated economic activities, equal to 82%. Research and Development Project, Urban and Rural Planning Optimization. Challenge, to develop optimal development plan for the land use in conurbated areas. Solution, High HRPO FOSSUM was developed as part of a high RAND, research and development, process oriented to the integrated modeling of the urban and rural connected regions. It integrate the experience of high and urban regional planning, master plans of resources for cities with FOSSUM, forest and agricultural sector optimization model, a dynamic model of nonlinear programming of the U.S. agricultural and forestry sectors that describes the dynamic allocation of rural land over time, as a result of competition from forestry activities with agricultural sectors. Result, implementation of prototype version of the model for a Latam city. Regional Economic Computable Equilibrium Model. Challenge, to model the economy in a conurbation, considering that cities correspond to a region within a country, so the study and modeling of its economy must be analyzed in the light of this inevitable peculiarity. Solution, design and implement a model considering that the country's economy is simply the starting point for modeling the region, but it must be adjusted to consider the economic relations derived from its regional character, which implies relations with other regions, that allow the free flow of products, people, and production factors. Result, implementation of a prototype model to simulate the multi-regional economy, based on a multi-sectoral equilibrium model. Location and sizing of social infrastructure model. Challenge, to implement master plans for the different facilities of the city. Solution, design and implementation of a DSS that integrates mathematical models to optimize several master plans that are part of the city development plan. These models include food supply, solid waste processing, public space, health facilities and educational buildings. Result, the DSS was delivered to the end user who must implement the information system to use the models. Solid Waste Transportation Model. Challenge, to implement a DSS for solid waste transportation. Solution, design and implementation of a set of optimization models considering two main processes for solid waste collection, house by house, and containers. For optimal solid waste collection, the model defines allocation of blocks to collection sectors, determination of the number of visits per collection sector, allocation of operational resources to sectors, definition of optimal paths within each sector, and planning routes, schedules and frequency of visit. Result: the model was delivered to a consulting firm. Food Supply Chain Master Plan. Regional food supply planning is based in models that simulate the supply chain of food to cities based on the optimization, design and operation of the logistics chain that is required for this purpose. Project: Regional Food Supply Master Plan. Challenge: to implement a mathematical model to optimize the Bogotá Food Master Plan, that is part of the Bogotá Development Plan. Solution: design and implementation of a mathematical model of the food supply chain, following the principles developed by the Mayor of Bogotá in the Study Plan de Abastecimiento de Alimentos para el Distrito Capital, y la Región Definitiva. The objective of the model is to guarantee the principle of food security, to ensure the availability and quality of food, to reduce the prices of supply, to facilitate the access of all citizens to a more adequate food, and build a supply system that ensures, around a basic basket that, in nutritional terms, allows adequate nutrition for the population. Result: a mathematical model to support cities' food master plans. In the case of Bogotá, the area of influence is not only concentrated in Bogotá, but also covers the 19 municipalities that make up the Sabana de Bogotá. The offer considered 9 production chains: beef, fruver, potato, milk and derivatives, groceries, grains, panela, eggs, and chicken meat. Research and Development Project, Regional Food Supply Planning. Challenge: implement a mathematical model to optimize food supply in Guayaquil. Solution: design and implementation of a mathematical model for the food supply chain, following the principles developed by the Mayor of Bogotá. Result: a prototype of the optimization model was developed and implemented, as part of a postgraduate thesis in ESPAL, Escuela Politécnica del Litoral, Ecuador. Decision-making: Artificial Intelligence and Disaster and Emergency Management. This is a project of research and development of special interest in hypothalamus artificial intelligence. The challenge: develop a DSS for disaster and emergency management. The overall objective is to minimize potential negative economic impact and human life losses. The solution: design a set of mathematical models to address the problems arising from disaster management based on stochastic programming models. The benefit: a set of measures and mathematical models to prevent and/or reduce the impact of disasters, and it prepares the community to respond in the best way when a disaster strikes. The general approach of HI is to connect predictive and prescriptive analytics models, which implies an integrated holistic vision, multidimensional space-time, of the entire supply chain of disaster response services. Predictive analytics is based, mainly, in artificial intelligence, machine learning, and complex probabilistic methods. Prescriptive analytics in mathematical programming, better known as optimization. Activities to ensure safety. These mission areas may be grouped based on when a defensive action is intended to occur, either before, during, or after an attack. Proactive planning. Mission areas whose defensive actions are taken before an attack occurs. These mission areas are prevention/protection and mitigation. Real-time operational planning. Mission areas whose required actions are taken during or immediately after an attack. These mission areas are detection and response. Recovery planning. Mission areas whose required actions occur after an attack. This mission area is recovery. Some cases studied by HI are Decision-making: Artificial Intelligence and Disaster and Emergency Management. Part 1. Events due to nature. Presents a summary of the studies conducted by HI. Decision Support System for Earthquakes Management. Challenge: develop a decision support system for natural disaster management. The overall objective is to minimize potential negative economic impact and human life losses. Solution: design a set of mathematical models to address the problems arising from natural disaster management based on stochastic programming models. For this purpose, the historical behavior of nature is studied by trying to know probabilistically what can happen in order to make decisions where, when, and how to allocate resources to mitigate and/or prepare for disaster. Synthetic scenario generation models for each type of disasters should be generated by field experts in the field. Result: the implementation of the DSS for Seattle. Implemented by the Seattle government. Sun Tzu, in the book The Art of War, said, "Every battle is won before it is fought." In the war on terror, planning supported by the scientific method can avoid conflicts, so that many battles are won without a fight. Decision-making, artificial intelligence, and disaster and emergency management. Presents a summary of the studies conducted by HI. DSS for Homeland Security. Challenge: develop a DSS for Homeland Security Management. The overall objective is to minimize potential negative economic impact and human life losses. Solution: design a set of mathematical models to address the problems arising from natural disaster management based on stochastic programming model and game stochastic theory. Result: the implementation of the DSS for the U.S. implemented by the U.S. government, for the oil sector. Autonomous real-time distributed traffic optimization. This is a project of research and development of special interest in hypothalamus artificial intelligence. Traffic real-time distributed optimization. Optimizing traffic light sync in a traffic system is a complex problem that joins complex areas with complex traffic networks. Solving the integrated problem, as a single problem, may be impossible. Splitting the problem by zones makes it easy to solve the total problem, and connectivity, based on principles of mathematical optimization, between the different problems, zones, ensures that the system walks the optimality path. Today's information capture intensive systems, smart metering, allow optimal operating conditions to change dynamically, as traffic behavior changes in the city. Challenge: using the Industry 4.0 environment to optimize the flow of vehicles in a large region. Solution: implement a mathematical model based on the concepts of autonomous real-time distributed optimization. This is the design of a DSS aimed at optimizing the dynamic synchronization of traffic lights in a traffic system. Optimizing traffic light sync in a traffic system is a complex problem, primarily in complex areas with complex traffic networks. Solving the integrated problem may be impossible. Splitting the problem by zones may make easy to solve the total problem. However, the dynamic nature of the problem, and its spatial dispersion, make attempting an optimal solution utopian. The connectivity between the different problems, based on principles of large-scale mathematical optimization, ensure that the system travels the path of optimality, close to the optimal solution. Today's information capture intensive systems, smart metering, allow optimal operating conditions to change the decisions dynamically, as traffic behavior changes in the city. From the traditional planner's point of view, the region can be seen as a single zone, which he, or she, want to optimize the traffic network, through a monolithic multi-period advanced analytical model. For a small town, it is possible that today's computers can solve the monolithic model, but for a big city it is impossible. It is possible to attempt to solve the monolithic problem using large-scale optimization methodologies, based on the partitioning and decomposition of the mathematical problem. To do this, the entire region can be divided into zones, each of them associating a multi-period subproblem. In turn, these subproblems can be divided into as many subproblems as periods, to achieve the highest level of atomization. Each zone may have its own control center, which may be a computer that collects signals from the zone, and solves the problem for that zone. This approach could increase the size of the region, but in the speaker's opinion, it will still be insufficient for large regions. Water Resources Systems Optimization. High water corresponds to the decision support system, especially oriented to the planning and operation of water resources. This SSD can be used alone or integrated with high power. High water allows any type of connectivity for the topology of the hydraulic system. Water Resources Planning and Scheduling Model. Challenge: to develop Water Resource Regional Planning Mathematical Model. Solution: design and implement a mathematical model of stochastic programming, using large-scale optimization technologies, that simulates multi-purpose water resource systems. The model was generally designed for use in medium-term planning activities, or in short-term operations scheduling activities. Result: the model dates from the early 80s, when PDC Ingeniería S.A. used, in Venezuela, the basic model in the following projects: Master Plan for Water Resources Zulia State, 1980, and Irrigation System Design Orituco Guarico, 1979. Project: Flood Control and Power Generation. Challenge: implement a model for the optimization of the design of a project for the use of water resources with a dual purpose, flood control, and electricity generation. Solution: design and implementation of a water resources planning model to be used in the study. Result: the model has been used in several research and consulting projects. The first project was the design of the Sinu River Project, to expand the generation capacity of the Ura hydroelectric power plant, carried out for the engineering consulting firm Gomez, Cajao e Asociados, in 2008. Project: optimal design of complex water resource systems for environmental control. Challenge: to develop a generic mathematical modeling framework for complex water resource systems, to be simulated using difference, or finite element models. Solution: design and implementation of a bi-level optimization model, which at the top level has an optimization model associated with strategic, and/or operational decisions, that determine the parameters, and/or boundary conditions, of a finite difference model, that represents the complex system of water resources, lower level. The interaction between the two levels generates information about the gradient of the objective function, for decisions associated with the finite difference model, to obtain the trajectory to the optimal point, for an objective function based on those parameters. Result: in 1979 and 1980, PDC Ingeniería S.A. used the model in the following projects: design of the Las Piñas Lagoon Protection System, and Irrigation System Design Orituco Guarico. The model integrates finite differences simulation models for subsurface water, and pollution in lakes and estuaries. Optimal design of water supply systems model. Challenge: to develop mathematical model to water resource distribution planning. Solution: design and implementation of a mathematical optimization model for the design and redesign of the aqueduct network, that supplies water to the city of Maracaibo. Result: the model dates from the early 80s, when PDC Ingeniería S.A. used the basic model in the project Master Plan of Aqueduct of Maracaibo City. A new version of the model was developed in a RAND project, realized as part of an undergraduate thesis in Universidad Industrial de Santander. The High Chief Scientific Officer advised the research. Project: optimal design water supply systems using pipes, tanks, and pump stations. Challenge: to implement a model for design water supply systems that includes pipes, tanks and pump stations. Solution: design and implementation of a mathematical model to optimize the design of radial water supply systems, pipelines and pumping stations. Result: PDC Ingeniería S.A. used the model in the several projects. Project: optimal design water drainage systems. Challenge: to implement a model for design water drainage systems. Solution: design and implementation of a mathematical model to optimize the design of water drainage systems. The optimization model is connected to a simulation model, which using kinematic wave theory, describes the dynamic process of water runoff along the drainage network. The simulation model is used to validate the results of the optimization model. In case of large differences, the optimization is boosted with the corrected maximum flow rates. Result: PDC Ingeniería S.A. used the model in the several projects. Project: streamflow forecasting. Challenge: to implement a model for short-term forecast river streamflow. Solution: design and implement a forecast model based on state estimation framework, Using the multi-state Kalman filter methodology, developed by the chief scientist of HI. Result: the model has been used in several research and consulting projects. Management of complex public projects. Planning and scheduling of large projects. Based on mathematical programming models that optimize the execution of large projects through the optimal allocation of project resources. Investment plan portfolio optimization. Optimization of decisions for the selection of investment or business plans based on a mixed binary programming model that contains the constraints associated with the logic of project selection processes that must respect constraints of different types, which can be social, economic, technical and/or government policy. The model must be stochastic optimization, in such a way as to make decisions that contemplate probable economic development scenarios, selecting a portfolio of business plans that, in terms of expected value and risk coverage, are the best according to the decision criteria of the organization. The objective is to determine the investment plan that allows balancing multiple objectives, such as maximize incremental sales, maximize the jobs generated, maximizing private investment, or minimizing extreme poverty. HI use large-scale optimization methodologies to solve the project management optimization problems. The image presents the conceptualization of a multi-level system to solve the problem when there is a need to coordinate more than one project. The project management optimization mathematical models developed by HI are project management optimization and optimal earthworks movement. Project management optimization model. Challenge: to implement a mathematical models for the optimization of the construction process. Solution: development and implementation of a mathematical model for the optimization of the construction process in the shortest possible time, and respecting constraints of budget, resources, etc. The model is based in continuous time modeling. Result: the model has supported planning the construction of a set of 9 buildings. Optimal earthworks in urbanizations and roads model. Challenge: to implement a mathematical model for the optimization of earthworks in construction projects. Solution: design and implementation of a mathematical model to optimize earthworks in the construction of housing estates and urban roads. The main objective is to minimize the costs of earthworks through the adjustment of the topography modified by the team of urban planners, taking as a reference the original topography of the land, and respecting technical and architectural, legal criteria and the criteria of the engineers. Result: PDC in HI area used the model in the several engineering projects. Research and Development Project, DSS Transmission Lines Project Management Optimization. Challenge: to design a DSS to management large transmission lines construction projects. Solution: design a DSS aimed at optimizing transmission line construction and/or maintenance projects. Result: HI has established a partnership with the National University of Columbia, Campus Medellin. Public Health Systems Optimization. Mathematical algorithms for epidemic management, based on high-complexity mathematical methodologies will prevent the most deaths. Public health management implies. Challenge: to design and implement a DSS to pandemic management. Solution: design and implementation of a DSS aimed at pandemic management integrated by the following high-complexity models. Epidemic Simulation Model. It simulates the spread of the epidemic as a result of a mix of control policies to deal with the epidemic, mitigation, confinement, and vaccination. Modeling divides the territory into regions, the population into socio-economic segments, and time in seasons, in order to have a dynamic epidemiological model including multi-infected states, multi-region mobility, and multi-socio-demographic segment. Epidemic Management Optimization Model. It optimizes control policies, the use of health supply chain, HSC, resources, the optimal expansion of HSC vital components, bearing reference to the Epidemic Control Policy Optimization Model, and the vaccination processes. Epidemic Socioeconomics Impact Model. It determines the socioeconomic impact of pandemic control policies on the economy. Integrated with our S/OPT, it can produce dynamic pandemic control strategies that balance those contradictory objectives that may arise in the epidemic management process, minimize human deaths and maintain the economic's health. And Epidemic State Estimation Model. Hybrid Predictive Analytics Model, based on the distributed Kalman filter, to track the pandemic. Pandemic Management Optimization Process implies research in the following areas: epidemic theory, smart sampling, identification of epidemic model parameters and the epidemic state, and mathematical programming optimization models oriented to control and management of the pandemic process. High Health integrates with high RPO, regional planning optimization. This implies that all models of the two systems can be integrated through the database, common data model, or by means of equations that integrate a unique holistic model, this following the principles of structured mathematical modeling. This integration is since the management of public health problem corresponds to regional planning problem, as experienced during the COVID-19 pandemic. Project, DSS Pandemic Management Optimization. Challenge, to design and implement a DSS to pandemic management. Solution, design and implementation of a DSS aimed at pandemic management integrated by the following models. Epidemic Simulation Model, simulates the spread of the epidemic as a result of a mix of control policies to deal with the epidemic, mitigation, confinement, and vaccination, dividing the territory into regions and the population into socioeconomic segments. Epidemic Management Optimization Model, optimizes control policies, the use of health supply chain resources, the optimal expansion vital resources, and/or the vaccination processes, and Epidemic Socioeconomics Impact, determines the socioeconomic impact of pandemic control policies on the economy. Result: this project was partially funded by CONACYT through the Technological Institute of Mexico, Ciudad Madero campus. Educational Systems Optimization. As part of the services offered are timetables for educational activities. It includes allocation of resources, teachers, classrooms, timetables for course exams, medium-term resource planning, student collection/distribution routing, assignment of students to educational institutions, location and capacity sizing of facilities, and food supply optimization. The mathematical models can be customized for special business rules of educational institutions. Project, School Timetabling Optimization. Challenge, to support decisions about scheduling and designing capacities of schools in Peru. Solution, design and implementation of a mathematical model to optimize the school timetabling process. Result, optimization services are selling under optimization on demand, so that high provided hosting services to solve the models, when the clients required the timetabling service. In 2012, the model was used by a client managing 19 schools. The resource savings were 1 teacher per school, average, which equates to approximately $1 million of payroll cost per year. Project, design of a university timetabling optimization model. Challenge, in March 2018, the Instituto Tecnológico de Monterrey hired the Bipragma High Alliance to design a mathematical model to support its decisions about the schedules of its 31 campuses in Mexico, where study around 70,000 university plus 30,000 school students. Solution, design of a set of mathematical models to meet the following activities: medium and short-term demand forecasting, aggregate resources planning, ideal timetabling scheduling, and adjustment of real timetabling. Result, the algebraic formulation of the models was delivered to a consulting firm, and to the university. It includes the solution process of the complex problems. A POC was developed using Optex, Optimization Expert System. Project, optimal location of educational facilities. Challenge, to advise the mayor of the city of Medellín on the development of master plans of social facilities, schools and others. Solution, design and implementation of a DSS municipal facilities location. The models consider the following decisions: installation of capacity additional, expanding the capacity installed, or creating capacity associated to new facilities. Uninstall social infrastructure determines whether uninstall facilities that are operating, and modernization of social infrastructure, technological conversion of older installations. This is a multi-criteria problem defined as a weighting sum of the total cost, investment plus operational costs, and access cost, time. The models produce a Pareto function of total costs versus access time. It is a measure of the service quality. A key feature is the determination of which demands are assumed by the supply service facilities. It is based on the McFadden-Rodham utility theory. Result: implementation of a DSS and use it for Medellin City. The optimization models were linked to the municipality's GIS. School bus routing optimization model. Challenge: to develop a routing model for collection and/or distribution of school students. Solution: design and implementation of a routing optimization model. Result: implementation of the model in a web server to be used as MOS, Mathematical Models as a Service. Special Projects Optimization. Project optimization of the dynamic planification of the process of massive registration of voters. In 2010, the Civil Registry for the Identification and Registration of Voters of Ecuador selected Costa Blanco and Asociados Consultores, in Guayaquil, and HI, to carry out a consulting project for the optimization of dynamic planning for the process of mass registration of voters of the Ecuadorian population.